You already know that an object in motion has a kinetic energy given by 1/2 the mass times the velocity squared. If a group of particles is moving together, the total kinetic energy will be the sum of all the individual kinetic energies. Now consider an object made up of a group of particles rotating about a fixed axis with angular velocity omega. The linear velocity of one of the particles is equal to the distance from the rotation axis times the angular velocity. Thus, the kinetic energy of a rotating object made up of a group of particles can be written as the sum over all of the particles' individual rotational kinetic energy, given by 1/2 times the mass times the distance squared times the angular velocity squared. We can define the moment of inertia of an object given by capital I to be the sum of each particle's mass times the distance of the particle from the rotation axis squared. With this definition, the kinetic energy of a rotating object can be written as 1/2 the moment of inertia times the angular velocity squared. Comparing the kinetic energy of linear motion with that of rotational motion, notice that the mass is replaced by the moment of inertia and the linear velocity is replaced by the angular velocity. The moment of inertia is a physical property of an object and is not only dependent on the mass, but also on the shape of the object relative to the rotation axis. Consider an object made up of 4 particles of different mass separated as shown. Let's calculate the moment of inertia of this object for 2 different rotation axes. For a rotation axis through the geometrical center of the object, we must multiply the mass of each particle times the distance of that particle from the rotation axis. For the given distances between the particles, what is the distance from one particle to the rotation axis? Correct. The moment of inertia can now be calculated by summing over all the particles to get 15 kilograms meters squared. What if the same object now rotates about a different axis? Let's calculate the moment of inertia for this case. The difference is that now the distance from the rotation axis to the particles is different. For example, the distance to the rotation axis for the particle through which the object is rotating is 0. What are the other particles' distances from the rotation axis? Correct. Now calculate the moment of inertia for this rotational axis by summing over all the particles. The answer is 32 kilograms meters squared. Notice that the moment of inertia of the same object rotating about a different axis is different. Qualitatively, a smaller moment of inertia implies that the object is easier to rotate. The moment of inertia can also be calculated for a solid continuous object. This can be done by dividing up an object into very small pieces, each with a mass delta m, and summing over all of the small pieces. In the limit that delta m goes to 0, the sum is replaced by an integral expression for the moment of inertia. Using the density is equal to the mass divided by the volume, the moment of inertia can be expressed as a volume integral, which is often a convenient form for calculating moment of inertia for a solid object. Let's calculate the moment of inertia of a thin cylindrical rod rotating about one end. We must first determine the volume element for a small section of rod. What is the volume of a rod with a cross-sectional area A and length L? Correct. Thus, if the rod is divided up into small pieces, each with a length dr, the volume of each piece is the cross-sectional area times dr. Now use this in the integral expression for the moment of inertia. Notice that the limits of integration are from the rotation axis at r equals 0 to the length of the rod at r equals L. Also, note that the mass, density, and area are constants and can be moved outside the integral. After integrating over r, substitute for the density, which is the mass over the volume, to finally get the moment of inertia of a thin rod rotating at one end is 1/3 the mass times the length squared. What if the rod is rotating about its middle rather than its end? How do you think the moments of inertia compared for each case? For the same rod, which sense of rotation has the smaller moment of inertia? Correct. To calculate the moment of inertia for the rod rotating about its center, use the same expression we found before. For this case, the limits of integration are different, going from the center to either end, which is from negative L over 2 to positive L over 2. After integrating and substituting for the mass density as before, the moment of inertia in this case is 1/12 the mass times the length squared. This case illustrates that the moment of inertia is smallest for an object when the rotation axis is at or near the center of mass. The moment of inertia has been worked out for various solid objects and can be found in the table provided. The parallel axis theory provides a useful method for calculating the moment of inertia of an object that is rotating about an axis different than from the center of mass axis. The parallel axis theory states that if d is the distance from the center of mass to the rotation axis, the moment of inertia is equal to the moment of inertia about the center of mass plus the mass of the object times d squared. Going back to the thin rod rotating about one end, we can calculate the moment of inertia using the parallel axis theory. The distance from the center of mass to the rotation axis is L over 2. Using this in the parallel axis theory, along with the moment of inertia about the center of mass that we previously found, gives I equal to 1/3 the mass times the length squared. Not surprisingly, this is what we had calculated before. In a previous section, the concept of torque was introduced, which is related to the application of a force causing an object to rotate. A formula was found stating that the torque is equal to the cross product of the distance vector from the rotation axis to where the force acts and the force vector. The magnitude of the torque is given by r times F times sine theta, where theta is the angle between the vectors r and F. We can substitute for the force using Newton's second law, which states that force is mass times acceleration. The product of the acceleration times sine theta is equal to the tangential acceleration of the object, which can also be expressed as the distance from the rotation axis times the angular acceleration. Now we have that the torque for a point object is equal to the mass times the distance from the rotation axis squared times the angular acceleration. If the force acts on a solid object, we can divide the object into small pieces, each with mass delta m. The torque acting on this small part of the object is given by delta m times the distance to the rotation axis squared times the angular acceleration. The total torque acting on the object is obtained by summing over all of the small elements that make up the object. In the limit that each piece gets smaller such that delta m goes to 0, gives an integral replacing the sum. Angular acceleration does not depend on the location, so it can be moved in front of the integral. Recognizing that the integral is simply the definition of the moment of inertia gives our final result that torque is equal to the moment of inertia times the angular acceleration. In vector form, this expression represents Newton's second law applied to rotational motion. Notice that when compared to the linear form of Newton's second law, that the torque replaces the force, the moment of inertia replaces the mass, and the angular acceleration replaces the acceleration. You probably remember the Atwood's machine, which is two masses connected by a rope over a pulley. Previously, we considered the pulley to be massless. Now let's take into account that the pulley has a mass and that the rope does not slip over the pulley. What is the acceleration? First, we use Newton's second law to describe the motion of each mass. Let's assume that the mass on the left is going down and the mass on the right is going up. Choosing up to be in the positive direction and down to be negative, which equation corresponds to Newton's second law for mass 1 on the left? Correct. Which equation corresponds to Newton's second law for mass 2 on the right? Correct. Notice that because the pulley has mass, the tension is not the same throughout the rope as it was in the massless pulley case. Thus, with Newton's second law for each mass, we see that there are two equations but three unknowns: the two different tensions and the acceleration. Another equation that can be applied in this situation is Newton's second law for rotation, which states the sum of the torques is equal to the moment of inertia times the angular acceleration. Looking closely at the pulley, the torque is provided by the rope on either side of the pulley. Since the torques act in the opposite direction, whichever one is largest will cause the wheel to spin one way or the other. Assuming the tension in the rope makes a 90-degree angle with the pulley at the contact point, which expression gives the sum of the torques? Correct. We can relate the angular acceleration to the linear acceleration using which expression? Correct. What is the moment of inertia of the pulley, which you can take here to be a solid cylinder with mass m and radius r? Incorrect. Check the moment of inertia table for a solid cylinder. Try again. Correct. We now have 5 equations that we can use to solve the problem. Substituting for the moment of inertia and the angular acceleration finally gives us 3 equations and 3 unknowns. We can use this system of equations to find the acceleration. What is the final answer for the acceleration? Correct. When the pulley has a mass, the acceleration is lower than when it is massless, since some of the energy now goes into the rotating pulley. The difference appears in the denominator, which now includes the pulley's mass divided by 2. We now consider the combination of rolling motion and translational motion. Two assumptions are made when we consider rolling motion. One is that the axis of rotation passes through the center of mass, and the other is that the axis of rotation always points in the same direction. When an object is rolling, it has both linear kinetic energy and rotational kinetic energy. Thus, the total kinetic energy of a rolling object is the sum of the two kinetic energies. Note that the linear velocity is the center of mass velocity. For rolling motion without slipping, there is an important equation that relates angular motion with linear motion. This relationship states that the velocity of the center of mass is equal to the radius of the object times the angular velocity. Equivalently, the acceleration of the center of mass is equal to the radius of the object times the angular acceleration. These equations are sometimes referred to as the rolling without slipping conditions. We now consider a solid sphere rolling down an inclined plane. Let's see if we can calculate the acceleration of the sphere as it rolls down. Note that the friction between the sphere and the surface is what causes the ball to rotate. Without friction, the ball would simply slide down without rolling. Since we are looking for the acceleration, the best place to start is usually Newton's second law. Taking x to be positive in the direction which the sphere is rolling, what is the linear force equation for the x component? Correct. What is the torque equation? Incorrect. The torque is the force times the moment arm equal to the moment of inertia times the angular acceleration. Try again. Correct. We have two equations, but we have three unknowns: the friction, the acceleration, and the angular acceleration. We can also use the rolling without slipping condition that states that the acceleration is equal to the radius times the angular acceleration. Now, given the moment of inertia of a sphere, what is the acceleration? Correct. The factor of 5/7 in the acceleration is due to the moment of inertia of the sphere. If the ball were to slide down the incline without rolling, the acceleration would be g times sine theta, and thus it would reach the bottom faster. This is because friction, which causes the sphere to roll, acts against motion and decreases the linear acceleration. The acceleration of an object rolling down an incline is dependent on the moment of inertia of the object. Objects with a smaller moment of inertia will have a larger acceleration. If the three objects at the top of the incline all have the same mass, which one would roll to the bottom first? Incorrect. One of the other objects has a smaller moment of inertia. Try again. Correct. We see that the solid sphere, which has the smallest moment of inertia of the three objects, reaches the bottom first. This result can also be found using energy considerations. Recall that the total kinetic energy of a rolling object is the sum of the linear and rotational kinetic energies. We know from conservation of energy that when the objects reach the bottom of the incline, the total kinetic energy will be equal to the gravitational potential energy, which is the mass times gravity times the height of the incline. Now use the rolling without slipping condition in the conservation of energy expression. From this expression, you can solve for the velocity of the center of mass when the objects hit the bottom of the incline. Notice that when the moment of inertia is larger, the final velocity is smaller, and thus the object takes longer to reach the bottom. This is because some of the energy is converted into rotational motion, and an object with a larger moment of inertia will have more rotation.